Good morning. Okay, so today we're going to keep going with functions. Functions part 2. I updated the notes on Moodle, so 2.6 is now in part 1 because we finished that last day, and then we'll start 2.7 and 2.8. They're big sections though, so I expect them to take all day today. And then we'll start, I think is it polynomials? Oh, we'll start quadratic functions next day, chapter 3, in a different textbook, but I get confused if I did the same material but from 2 different textbooks. So anyways, just a quick review. If you guys wouldn't mind at some point, let's see if I can get back into Moodle here. Whee! Here, you guys. I put some assignments up for each of the sections. Now, all of these are very small. I think 2.1 is the biggest one because that's where we kind of introduced function notation and we talked about domain and we did all those kind of core things in 2.1. And then the assignments are very, very small for 2.2, 2.3, 2.4, and 2.6, and 2.5. I don't know why I didn't say that one. So hopefully those will work. I think it does that weird thing where it tells me I don't have an authorized session, but for you guys it worked before, so morning now. So hopefully those work for you guys. I put the due date as November 3rd, right? Just checking my calendar here. Yeah, Tuesday, November 3rd. So let's say chapter 2 assignments posted on Moodle are due November 3rd. I guess I should put the year, I don't know. This year. 11:59 p.m. So essentially midnight, but just so there's no confusion, 11:59. So that's Tuesday next week. So you've got some time to work on those. Like I said, they're very, very small, and just so we get some practice in. Right? Okay. Let's see about review. Oh, and I also posted, if we go back to Moodle here, I also posted the chapter 2 solutions, 2.1, 2.2, and those are from the notes, right? So they're not the assignment solutions, of course, but they will help you do the assignment. So, so that's why I posted those. All right. For a quick review, right, we were still talking about functions. We were talking about things like when is it increasing or decreasing? By definition, right, if A is less than B and f of A is less than f of B, then you've got this increasing function. If f of A is greater than f of B, then you've got a decreasing function. But we said, well, just if we have the graph, then we know what increasing looks like and what decreasing looks like, so we don't really need that definition, right? But it's nice to introduce that definition because things like that can be hard to read, so it's nice when we know what it's talking about and we can say, oh, okay, well, that kind of makes sense because I know what increasing looks like, right? Increasing, decreasing. And so we can kind of make that link between the definition of increasing and decreasing and what we already know. So then we talked about, okay, well, if a function is increasing and then at some point it changes to decreasing, then what we call that is a local maximum, right? So then we talked about local maximums and minimums, right? So we applied that definition of increasing and decreasing, and we said, all right, well, I can find maximums because that's where it changes from increasing to decreasing, or minimums because that's where it changes from decreasing to increasing, right? And so that's how we found local max and mins. Then we talked about the average rate of change. Average rate of change, which is f of b minus f of a over b minus a. Right? How much did the output values change? So how much did the y values change over how much did your x values change, right? And so your average rate of change is also, this is the net change over b minus a, right? Net change we introduced earlier, but just so it's there. We also said, well, one clever thing that we could keep in mind is that linear functions, right, so straight lines, they have a constant rate of change, and it's the slope. So linear functions have the slope as their constant rate of change, right? Oops, rate of change. So the slope is going to be the rate of change, and it just happens to be constant because if you think about a straight line, it doesn't matter. The net change is going to be the same on the same interval, and so you have the slope is the average rate of change for linear functions. So that's pretty handy. What else did we talk about here? Linear functions, not much. Then we went on to transformations. And summarize them all because it'll take half the day. Right, we can talk about vertical shifts, horizontal shifts. We can have vertical stretching or shrinking, right? So stretching, shrinking, and then we can have horizontal stretching, shrinking. We can have reflections around the x-axis or the y-axis. Let me just make sure I'm not missing anything. Yeah, reflections around the x-axis, around the y-axis. And then we talked about even and odd functions, right? So even functions are symmetric around the y-axis, and odd functions are a little bit weird because they're symmetric around the diagonal. But then we thought about, okay, so if an even function has the highest power of an even function is even. So if we talk about x squared, for example, then we have this parabolic shape. I'm trying to so that would be symmetric around the y-axis, right? Whereas if we have an odd function, so x to the power of 3, for example, then we get this, this kind of dancing motion, which is an odd function. So today, we're going to start in 2.7. So the notes for 2.7 here, where are they? Probably over here. Okay. So in 2.7, we're going to be combining functions. Now, combining functions are things like, okay, well, if I have a function f and if I have a function g, I can find a new function called f plus g where I'm just adding these functions together to make a new function. So, oops. Do this. Okay. So here, what we'll say is, if we have a function f and g, right? Or I should say if we have functions. That looks weird. Normal file. So if we have functions f and g, we can combine them to create a new function. So what these things look like, right? So f and g are functions, and they each have, so f has a domain of A, and g has domain B. So then we can find functions f plus g, f minus g, f times g, and f over g. And how they're defined is just exactly what you probably would want to do. If I had just asked you to find f plus g, then what would you do? You'd probably just add those two functions together. And that's exactly what we're doing. So how we denote it is my new function is called f plus g, right? So f plus g of x, right? They have the same variable. We're just going to write it as f of x plus g of x. Now the thing is, they have a domain, right? Because f is going to have some domain, so some possible inputs, and then g is going to have some domain. But really, the domain of f plus g can only be the shared space, right? So it's the overlap of the two domains. Overlap of the two domains. Notice that once you have A and B, right, it's going to be the same for the first three. The only time that it changes is that because we can't divide by 0, we also have to make sure that g of x is not equal to 0, right? So it is A and B again, just like before, with the added restriction of, okay, as long as g of x is not equal to 0, right? So there's going to be that added constraint. But besides that, right, if we're just adding, subtracting, multiplying, dividing functions, it behaves exactly the way you want it to, right? F of x plus g of x, f of x minus g of x, f of x times g of x, f of x over g of x, right? And then you just need to keep track of the domains for each of them, but they'll be the same. So here, let's do some examples. Which one should we do? So here, we're supposed to find f plus g, f minus g, f times g, and f over g, and their domains. Okay? That means that we first have to find the domain of f and the domain of g, and then find A and B. Okay? So let's do one with kind of a sneaky, well, okay, let's start nice and slow. Let's do 7 first. And then we'll probably do, let's do 13 next. Okay. So if you scan these, all of these functions, as soon as you have a square root or you have a fraction and you have an x in the denominator, that's when you're going to have restrictions on your domain. Otherwise, your domain is just going to be the set of real numbers, so any number is possible as soon as you see a root x. So everything here, all real numbers, and then that's why I picked this square root and this square root here, because we're going to have to restrict our domain a little bit. Same thing here, right? We would have to restrict our domain because we've got x's in the denominator, and we can't have x where the denominator is 0. So we'll start with 7, and we'll just copy them down here. F of x is x, and g of x is 2x. If we let A be the domain of f of x, right, then A is the set of x in the set of real numbers. There's lots of ways that we could do that. In fact, maybe I should do x given that x is in the set of real numbers, or such that. So the domain here, right, if f of x is just x, x can take on any number. There are no illegal numbers. Same thing with 2x. And so here, if we let b be the domain of g of x, then b is the set of x's such that x is in the set of real numbers. So what we can do before we even start combining these functions is we can find a and b, because we know that a and b is going to be the domain for all of these. Right, and so if I find them once, then I don't have to do it again, right? And so remember, A and B is the overlap of the two domains. So A and B is going to be, well, here I can have any number, and then here I can have any number. So of course, A and B is the set of x's such that x is in the set of real numbers.
Is that an answer? Like that's the final answer?
For the domains, yes.
Okay.
So
what's the weird like equal sign?
The weird, oh, in the set. Do you mean this one?
Yeah.
Yeah, so this is in the set.
That's what it means. Okay.
Yeah. Okay. So it's like a C with a, it's like one of those fancy E's. I don't know where they use them, but like trademark stuff. I don't know. I think I've seen them there, but anyways, okay. It's like a C with a line in it.
Yeah, cool. Thanks for explaining.
No worries. Good. So this is the domain for the first 3 that we're going to find. So let's go ahead and find f plus g of x, f minus g of x, and f times g of x. So f plus g of x, I don't love this notation, so luckily for me, this translates to f of x plus g of x. So now we're combining these functions, and I know what f of x is. F of x is x, and g of x is 2x. So this becomes x plus 2x, which we can simplify to 3x. So now notice what we've done here. We've managed to make a new function, f plus g of x, which is 3x, right? It's just a combination of f of x and g of x. So now we're going to do the same thing for f minus g of x. Just by definition, that's the same as f of x minus g of x. X minus 2x. Notice that g minus f of x would give us a different function, right? Just because of how subtraction works. So it's important that we use the same order, right? And so x minus 2x puts me at negative x, right? Whereas if I had g minus f of x, right, the domain would be the same, but I would have 2x minus x, which would just be x, right? So there's makes a difference. Do it on this next page. F times g of x is the same as f of x times g of x, which is going to be x times 2x, 2x squared. Right? So, and then the domain for each of these is going to be a and b, but I'll make a note here. Domain is a and b. Domain is a and b, right, where I've defined a and b here. And here the domain is a and b. The division is a little bit trickier, right? Because f over g of x is f of x divided by g of x. Okay. F of x was x divided by g of x, which is 2x. X divided by 2x is really just 1 over 2. And so the domain here, because we've got this x here, so even though you end up at 1/2, right, you want to exclude x equals 0, because you wouldn't actually get to the 1/2 if g of x was equal to 0. And so here, the domain is a and b excluding values where g of x equals 0, since we cannot divide by 0. So the domain here, g of x is 2x, so 2x can't be 0. G of x equals 2x, which cannot be 0. So x cannot be equal to 0, right? So we have to exclude that from our domain. So what we can do is we can say, well, the domain is the set of x such that x is in the set of real numbers, but also x is not equal to 0. So let's do a little bit harder one. We'll do 13. I'll go snag it here. Oops. Way too big. Okay. So what I'm going to do is I'm going to find the domains of each of these. That's where I'm going to start. And then once I have the domains, then I can go ahead and combine these functions. So if A is the domain of f of x, let A be the domain of f of x. The domain of f of x, remember, if we've got square roots, we can take the square root of everything but negative numbers, right? So as soon as this thing becomes negative, then it's not in the domain anymore, right? So 25 minus x squared can't be negative. So what we've got here is 25 minus x squared has to be greater than or equal to 0. And so what we can do, right, we can add x squared to both sides. As long as we're adding, we're okay. We don't have to switch the sign, right? So we've got 25 has to be greater than or equal to x squared. Once I take the square root, though, I have to be careful because then I get the plus minus version of, so plus minus the square root of 25 has to be greater than or equal to x. So now x has to be less than or equal to plus minus 5, right? The square root of 25 is 5. So we get plus minus 5. They have to be greater than x. So what does this look like? Right, if x has to be less than plus minus 5, less than or equal to, it makes sense, right? Because if I plug in 5 here, positive 5, I get 5 squared, which is 25. 25 minus 25 is 0, so that's fine. Same thing if I plug in negative 5 here, negative 5 squared is also 25, so 25 minus 25 is 0. So what this tells me is that, let's see here, how do I want to show this? My x's can be between positive 5, or from negative 5 to 5. How do I want to show that? Negative 5, oops, negative 5 let's see if that works out. It's right. I just want to make sure that I can justify this. Because if you try something, x has to be greater than, anyways, this is correct. If you try something like negative 6, put your negative 6 in brackets, for example, squared, 36, 25 minus 36 is negative 11. If you try to take the square root of that, it's not going to work, right? And so your x has to be between negative 5 and 5. And so that's going to be your domain. So the domain, oops, A is the set of x's such that x is between negative 5 and positive 5. I'll stew on it for a little bit. Why? It's too early. Why is it? Anyways, this is correct, so don't worry. But I just wanted to be able to justify why I switched it. It's just like a thing that I did. Yeah, so the reason it's right is because we can't have a negative here. But how did I get there? How did I know? So then, yeah, Desmos, that's true. Yeah, you should always just check your work with Desmos, just make sure. So let's see here. Let's find the domain of this thing. Again, x plus 3 has to be greater than or equal to 0. And so if we let, how would I just scale this down just a smidge? And then let B be the domain of g of x, then we're saying x plus 3 has to be greater than 0. So x must be greater than or equal to negative 3. That one's easier to handle. So is the set of x's such that x is greater than or equal to -3. For A and B, we're saying it has to be the overlap, right? So what I find is easiest is we have to figure out where these two things overlap. So I use a number line often, unless it's obvious, right? Then you don't have to, but I'll put 0 there, and then I've got -3 as a touch-in, kind of a check-in point. -5 and +5 are check-in points as well. So -5 and +5. So I'll use green to show where A is. So A is saying X can be anywhere, including -5 and +5 and anywhere in between. And then for B, I'll use pink for B. X can be anything as long as X is greater than or equal to 3. Sorry, -3. So here it can be equal to -3, but it has to be greater than -3. So that keeps going. In fact, I'll make it clearer. There. So now, these are all closed dots, right? So that's something that we need to keep in mind. Let's say A and B is going to be in orange here. So the orange has a closed dot here and a closed dot here at 5. So that's the overlap. So it's going to be the set of x's such that x is between -3 and 5. Let's just check this first one, because it kind of gave me some grief. 25 minus x squared and then square rooted. Let's graph it in Desmos like Tim suggested. So I have the square root of 25 minus x squared. So my domain is from -5 to +5, right? And I have this semicircle, right? So it checks out, right? We're saying, okay, x can be anywhere between -5 and +5. And then if you check, right, also do the square root of, was it x minus, no, x plus 3? Pretty sure. Let's see here. Yeah, the root of x plus 3. Well, then the domain is all the values where x is greater than -3. So we've done it right, and we can confirm using Desmos. So that's good. The overlap of these two is going to be from -3 up to +5 inclusive, right? All closed dots. If we had an open dot here, we'd have to reflect that in our overlap. Yeah, so I think it has something to do with the negative, but anyways, just always confirm. If you're running into trouble here, right, then just confirm with Desmos. I'll have to check in on why I knew to do it, but I don't know why I knew to do it. That's the problem. So anyways, good. Okay, so we found the domain of, oh yeah, well, all your tests and stuff are just at home, right? So definitely use Desmos. use whatever you've got, right? So definitely get used to using it so that you know how to check your work when it's test time. Okay. I'll still want to see your work like this, right? But definitely just check your work using Desmos. Make sure it makes sense. Okay, so we found A and B. So this is the domain of f of x plus g of x, f of x minus g of x, and f times g of x. And then we have the added condition that the root of x plus 3 can't be 0 in the division, but we'll get there. So let's talk about f plus g of x. That's the same as f of x plus g of x. F of x in this case is the square root of 25 minus x squared plus the root of x plus 3. So there's nothing really I can do here because I'm adding the roots. So I'm just going to leave it like this. So the domain here is A and B, which we established just here. X is between -3 and 5. Same thing with f minus g of x. F minus g of x is just f of x minus g of x, which is the root of 25 minus x squared minus the root of x plus 3. And again, the domain is A and B. And then f times g of x is f, then I say f, but I wrote g. F of x times g of x. Now I've got the root of 25 minus x squared times the root of x plus 3. Because I've got the square root times a square root, what I can do, clean this up a little bit, is I can combine these, right? Because I can write this as 25 minus x squared to the power of 1/2 times x plus 3 to the power of 1/2. If I have the same power, I can combine them inside that same power. And so what this becomes is I get the square root of 25 minus x squared times x plus 3. And I can expand this out if I want to. You don't really have to, but let's do it just because. 25x plus 75 minus x to the 3 minus 3x squared. And then just to get in the habit of writing these things with decreasing powers, I'm going to rewrite this as negative x to the 3 minus 3x squared plus 25x plus 75. So now I've got what looks like a completely different function, and that's the whole point. So we're just combining these functions using addition, subtraction, multiplication, division. So now f over g of x is f of x over g of x. Oh, and I guess I should say, we know that the domain here is A and B. Right? The only time it changes is here in the division because we also need to ensure that g of x is not equal to 0, right? Which is just a slight tweak, right? So f of x was the root of 25 minus x squared over the root of x plus 3. So again, I can combine these under the square root if I wanted to, just using those exponent laws, right? So I've got 25 minus x squared over x plus 3, I don't think I've got anything that I could cancel here, so I'm just going to leave it as is. Right? You could factor out the 25 minus x squared, right? It's a square minus a square, but I'm just going to leave it. But here's my new function, also looks way different than the original two functions. So here, the domain is A and B excluding where g of x equals 0. Okay, so g of x is the root of x plus 3, and so it can't equal 0. So now we're saying, okay, well, I can square both sides, so I get x plus 3 cannot be 0 squared. 0 squared is just 0. So x cannot be negative 3. So all we have to do up here, and we kind of knew this all along, right? If we don't want it to be equal to 0, we just have to alter it so that x is just greater than negative 3. So the only thing that changes here is that this becomes an open dot, but everything else stays the same. So it's A and B, but then pull out the point where g of x equals 0. So now we're going to alter this just slightly for the domain. So the domain is the set of x such that x is just less than negative 3, or sorry, greater than negative 3 and less than or equal to positive 5. Good. All right. Not seeing any questions. So that's good. So let's keep going. Let's talk about the composite of a function or two functions. So here, we're saying that we're combining these functions. It's really just algebra of functions, right? So f of x plus g of x, we're just adding, subtracting, multiplying, dividing. Whereas here, and there's some extra domain practice here, but I'll leave that for you guys to do, because I want to talk about the composition of functions, which is going to be probably very new to you. So if we have two functions f and g, then the composite function f composed with g, which is also called the composition of f and g, is going to be f composed with g of x is the same as f of g of x. Okay, so let me copy this in here. Put it on a fresh page. Okay, so here, f, and then it's just a little dot in the, or an open circle in the middle. So this is read as f composed with g. Okay. Yeah, it looks like fog. F-O-G. And I actually read it as f of g, even though it's technically incorrect. But it becomes f of g of x anyways, and so that's why I find it a little bit of a mouthful to say f composed with g, but just remembering that f composed with g of x is where you put g of x into f. So wherever you see an x, you're going to replace it with g of x. We've actually done a few of these already, sort of, but we haven't done them like this explicitly. So here, f composed with g of x is the same as f of g of x. Yeah, so f of g of x, because it's like the most intuitive way to read this thing, but it's technically f composed with g of x, but because it just puts us here at f of g of x, it doesn't really matter. So here what this says is we have to replace each x in f of x with g of x, right? So we're putting a function into a function. So it can be a little bit tricky, but just like with, we did the difference quotient, for example, right? The difference quotient, I'll erase this in a little bit here, but that was f of x plus h minus f of x. Well, x plus h could have been g of x, right? And so then g of x going into f of x would be f of x plus h. But like I said. So I'll steal some of these problems here. So which ones should we do? Let's do, we'll do 48 first. Okay. And we didn't talk about the domains. Where's the domains? For these, no, I'm gonna pull the plug on the domains here. You can do it. In fact, I should probably do like a lighter color here. But I'm not going to emphasize it. We've spent so much energy on the domains already that for this, let's skip it. Oh, got a little, there. So let's just skip it. And if you're able to do it, then that's great. Right, the key thing is if you're putting g of x into f of x, if there are restrictions on the domain of f of x, then you have to apply those restrictions to g of x. But I try the domains on your own, but I will not emphasize it for compositions, right? Everything else I will, right? We do spend a lot of time talking about domains and things like that. But for compositions, yeah. And I know that's bad of me, but I just want to get the idea of compositions. So if we do 48, f of x is 6x plus 5, and g of x is x over 2. So we're supposed to find f of g, g of f of f, and g of g. All of these are going to be different, right? So let's have a look here. F composed with g of x. Like I said, I'll always probably just start writing it as f of g of x. And there are two different approaches that you could do, right? You could leave it as g of x, and so just write out f of x, replacing the x's with g of x, or you could just substitute g of x straight into f of x. That's kind of skipping a step, so I'm not going to do that immediately, but if you want to do that, that's totally fine. So then we have 6 times g of x plus 5, right? Plugging in g of x wherever I see an x in f of x, because that's what this is saying, right? So this is not very telling, but this, how we rewrite it, that's very telling, right? So 6 times g of x plus 5, and then now I can replace g of x with x over 2, keeping in mind that it's one thing. So 6 times x over 2, then plus 5. Okay. So 6 times x over 2 becomes 3x and then plus 5. So that's going to be f composed with g of x. And so this is my new function, right, which looks quite a bit different from f of x and g of x, right? And so now I've developed a new function, and that's just what we're doing today. So the next thing we wanted to do, I've got it here, g composed with f of x, which is now g is on the outside and f of x is getting stuffed in. So here, g of x is x over 2. So instead of x, oops, I'm going to write f of x divided by 2. F of x is 6x plus 5 divided by 2. So I get 3x plus 5 over 2. Remember, this 2 divides the 6x and the 5, right? So that's why it's 6 divided by 2 is 3x, and then 5 over 2 has to stay 5 over 2. The next one we wanted to do was f composed with f of x. A little bit strange, right? But it becomes f of x. So f of x is 6x plus 5, right? But I'm going to replace x with f of x. And so I get 6f of x plus 5. Right? But then remember, f of x is 6x plus 5. So what I get here is I get 6 times 6x plus 5 bracket and then plus 5. Okay. So I get 36x plus 30 plus 5, 36x plus 35. Now, for the last one, g composed with g of x is g of x. G of x is x over 2. So I have g of x divided by 2. G of x is x over 2, oops, divided by 2. Now I can use properties of fractions, right, which we've worked a lot with. I've essentially got a fraction over a fraction. 2 divided by 1, if you want to visualize it like that. X over 2 over 2 over 1. Flip and multiply. So this is going to simplify to x over 2 times 2 over 1 flips to 1 over 2. So this is x over 4. What's another one that we can do? Maybe 57. It's going to be nasty, but we may as well do it together, right? Copy. Just bring it in here. Okay, so I've got f of x. Notice that there are two places of x, right? X over x plus 1, and then g of x is 1 over x. So I'm dealing with two fractions. I can already tell that this is going to be pretty nasty, putting fractions into fractions. So it's going to require a lot of fraction work, of course. And so here we go. F composed with g of x is f of g of x. So I'm going to put in f of x, but instead of x, I'm going to write g of x. So I have g of x over g of x plus 1. So now g of x is 1 over x. So I'm going to be really careful when I'm replacing g of x with 1 over x, because it's 1 over x over 1 over x plus 1. In order to add these, right, I have to have a common denominator in order to add them and in order to simplify a fraction over a fraction. So this becomes 1 over x over 1 over x plus 1, and then I'll show it times x over x, right, to get that common denominator of x. So this becomes 1 over x over 1 plus x over x. Now I've got a fraction over a fraction, right, which I can flip and multiply. And so I get 1 over x times x over 1 plus x. Put those in brackets just to show that they're one thing. Multiplying here, x over x is going to cancel out, so I'm just left with 1 over 1 plus x. So that's my new function, f composed with g of x. So it gets worse before it gets better, right, when we're simplifying these fractions. Then we wanted to do g composed with f of x. G of f of x. Okay. G is just 1 over x, and replacing x with f of x, I get 1 divided by f of x. But f of x is that big nasty, and I'll copy it from my side here. 1 divided by x over x plus 1. Okay. So what I can do, right, is I've essentially got a fraction over a fraction again. So I can simplify this and say, well, this is the same as 1 over 1 times x plus 1, put that in brackets just to show that it's one thing, over x, which is just going to be x plus 1 divided by x. These are very different functions, right? But we're composing functions. How about f composed with f of x, which is f of x? F of x is that big nasty. So let's x over x plus 1. All right. I get f of x over f of x plus 1. But f of x is another fraction, x over x plus 1 divided by x over x plus 1, then plus 1. Okay. Notice that in order to combine these and in order to simplify stuff, I need to have a common denominator of x plus 1 because this is over 1. So 1 times x plus 1 is just x plus 1. And so I need to multiply this by x plus 1 over x plus 1 before I can combine these things. And so I get x over x plus 1, oops, divided by, now I can add across the top here, x plus 1 times x plus 1 is just x plus 1. So we get 2x plus 1 divided by x plus 1. So now I've got, and I'll put this in brackets too, a fraction over a fraction. Again, I can flip and multiply. And so I've got x over x plus 1 times x plus 1 times 2x plus 1. What's nice here is that the x plus 1 and the x plus 1 are going to cancel because they're multiplying. And so what I have is I have x over 2x plus 1. Okay. And then finally, if we do g of x, g composed with g of x is g of x. G of x was just 1 over x. So this becomes 1 over g of x, which is 1 over x, which is really just 1 over 1 times x over 1, which is x. Okay. So fractions, they're so important that we know how to deal with them. You want to pay a lot of attention to it. Okay. So here, down here, you're given a function and you're asked to kind of boil it down to what these two functions could be. And there are usually a couple of different options. There are some more obvious than others, right? Let's just steal some of these. We'll just do 1 or 2 here. Okay. So we want to express it in the form of f composed with g. So g is going into f. And so let's do 65. And like I said, you can make this kind of complicated or you can make it just nice and easy. And so if g of x, so capital G of x is f composed with g of x, right? Then we can let, I'll just say what it is here, is x squared over x squared plus 4. One obvious thing is it looks like I've replaced x with x squared, right? Wherever I see an x, I replaced it with x squared. So if I let g of x be x squared and f of x is x over x plus 4, then that's what's happened here. So if I let f of x be x over x plus 4 and g of x be x squared, then f composed with g of x is going to be this thing, right? So sometimes it's going to be useful to be able to look at something like this and see, okay, well, can I pull it apart into 2 different functions that have made a composition? Right? And so let's do 66 too. Capital G of x is 1 over x plus 3. Right. you could do something silly like g of x is x, but let's not do that. Let's say let f of x be 1 over x and g of x be x plus 3. Then f composed with g of x is wherever you see an x here, you're going to replace it with g of x, and then x plus 3 takes its place to make 1 over x plus 3. So here, down in the optional section, I'm saying it's optional because I'm not going to test you on something like this. It's way too long, but it is really good practice, right? If you have to do a composition, so we can make a composition of, what are those dolls, those Russian dolls that go inside each other? I guess maybe they're called Russian dolls. Anyways, H can go into G, G can go, and then that G of H can go into F, right? And so here we can compose with as many Russian stacking dolls, thank you. Right, we can stuff as many functions inside these functions as we want. It's just gonna get complicated very quickly, right? And so looking at this one, we're not gonna do it per se, but if we wanna find F composed with G composed with H, well, that means in G, I need to replace my x's with x plus 1. So that's going to be the root of x plus 1. Fine. Then I'm going to stuff that in for x into f of x. So then I get the root of x plus 1 and then overall minus 1. So that one's pretty simple, but because I've labeled it optional, let's leave it at that. And then same thing, right? We could have a composition of more than 2 functions. And so we can work backwards and just kind of say, okay, well, if I've got 3 functions that are composed in here, then I can break it down and see what I could split this function into. So that's 2.7. Don't worry, we're gonna keep going with function composition in 2.8. Because it actually plays a big role in one-to-one and inverse functions. So now we're going to talk about inverses. All right, so first things first. I'll start on a fresh page here. So 2.8, one-to-one. What's it called? One-to-one functions and their inverses. So one key thing is, so we're going to talk about the inverse of a function, which you know, in the simplest case, you just invert it, but the inverse of a function is actually a little bit more complicated than that. So we're going to try to find the inverse of a function. But the key thing is that a function only has an inverse if it's what we call one-to-one, which means that each input only maps to one output and one output only maps to one input, which is separate from the function. So something can be a function as long as it doesn't have 2 outputs for the same input. But now we're saying, nope, we can only have one input makes one output and one output makes one input. So we're going to talk about what that means mathematically for us. But just here, it's an important note. A function is only invertible if it is one-to-one. Therefore, before finding the inverse, we need to be able to show that a function is one-to-one. We need to be able to show that a function is one-to-one. Okay. So I'm going to go and steal this definition of a one-to-one function, and then we're going to talk about it. So the definition of a one-to-one function, it says that a function with domain A is called a one-to-one function if no two elements of A have the same image. So that means that if f of x1 is not equal to f of x2, so the output of x1 is not equal to the output of x2, it means that x1 can't be equal to x2. So how do we show this? So to prove a function is one-to-one, we let x1 equal x2. So we let x1 equal x2, okay, and say, or sorry, f of x1. There, big difference. And then show that x1 must be equal to x2. Okay. Instead of x1 and x2, I like to use a and b, right? But I'll just make a note here. I like to use x1 equals a and x2 equals b. So what does this look like? Let's grab some of these here. So if we have to, so determine whether the function is one-to-one. Okay. If I'm looking at something like maybe 14, start off nice and easy here. F of x is 3x minus 2. So what I'm going to do, right, so to prove a function is one-to-one, we let f of x1 be equal to f of x2. So, and I like to use a and b instead because it's cleaner to read, right? So what I'm going to do is I'm going to say f of a equals f of b, right? So here, let f of a be equal to f of b, and then show that x1 must be equal to x2, where x1 is a and x2 is b, right? So show that a must be equal to b. So how this is going to work is you've got f of a, that's 3a minus 2, is equal to f of b, which is 3b minus 2. Now, it might feel obvious that these two things, a is going to be equal to b, but that's not always going to be the case, especially if you have an x squared or an even power in there, it's not going to be the case. So just be careful. So you have 3a minus 2 is equal to 3b minus 2. Okay. All right, so now I'm going to go ahead and I'm going to simplify some stuff here. I'm going to add 2 to both sides, so that goes away. 3a minus 2 plus 2 is 3b, so 3a is equal to 3b, so a is equal to 3b divided by 3, so a is equal to b. Therefore, right, because we were able to show that if f of a is equal to f of b, that means a is equal to b. That's the reason that I can conclude that this thing is one-to-one. So this function f of x is one-to-one. So therefore, f of x is a one-to-one function. Now, we don't do a lot of proofs in this course, but this is one of them, and it's just kind of nice and flows nicely. Okay, let's do anything here, I'll make a note, right? Anything with an even power even powers are not one-to-one. Okay. Because what this is actually saying, right, is that you can't have the same output if x1 is not equal to x2. So that means if you have something like x squared, for example, here, right, then we can say, okay, well, I've got x1 and x2 here. F of x1 here is the same as f of x2, but x1 is not equal to x2, so it's not one-to-one. Okay, so it's not one-to-one if you've got these even powers. So really useful. If you're able to graph all these, right, then you'll know by looking at them if it's one-to-one. So the only one that I'm a little bit skeptical about is the 1 over x squared. So what I'm going to do is I'm going to graph it 1 over x squared. Notice here that there are restrictions on the domain, probably making it one-to-one. And so you'll want to make sure that you look at just those domains. But for now, what I want to do is I want to graph 1 over x squared to see what it looks like, right? So, because it's not really in my roster of things we know. So 1 over x squared looks like this. So one problem that I'm seeing right here, let's say when x is 1, the output is positive 1. But also when x is negative 1, the output is also 1. So I get the same output for different values of x, so it's not one-to-one. So we've already seen that this little guy is not one-to-one. What if we look at these ones? So let's look at 20, just graphically. X to the 4th plus 5. X to the power of 4, and then step it down, plus 5. Okay, so here, right, it doesn't look good if I wanted to have x equal to 1, probably. I get an output of 6, and here, same thing. If I have x equal to negative 1, I get an output of 6 again. So it's not one-to-one overall, but let's look at the range that they've given us. I'm only looking between x equals 0 and 2, right? So inclusive of 0 up until positive 2. So on this here, here's x equals 0, and then I'm going to trace it all the way up to x equals 2. And so for here, I only have one input for each output value. And so graphically, right, even though overall this function is not one-to-one, on the 0 to 2 range, it is one-to-one. So let's look at so for 20, f of x equals x to the 4th plus 5 when x is between 0 and 2. Okay, so in Desmos, it looks something like this, right? So overall not one-to-one. 0 to 2, let's say here. But between x equals 0 and x equals 2, it is 1 to 1. So you can do it graphically, but if I ask you to prove if a function, so here it just says determine whether the function is 1 to 1. This is how we prove that it's 1 to 1. So if I wanted to show, let's see here, I wanted some fractions. Oh, 24 maybe. So 24, I have f of x is 1 over x. So prove it is 1 to 1. So I have f of a equals f of b, and we're going to do more when we get into the inverse. But so f of a equals f of b, that's the same as 1 over a is equal to 1 over b. If I have to simplify this, I'm going to multiply my b over here. So then, and then multiply my a over here. So this becomes a is equal to b. Well, maybe I should show more work. 1 over a times b is 1. B is 1 times a. B is equal to a. Therefore, f of x is 1 to 1. So we've got this horizontal line test, right? So a horizontal line goes like this. So for the vertical line test, we were checking to see if we have a function, right? Because we can only have one output value per input. But now for 1 to 1, we're saying, okay, well, each input or each output value can only have one input. All right, so the horizontal line test is just used to see if a function is 1 to 1. And if we put it back in here, so here, if you have some sort of function like x to the power of 3-ish, right? So here we have x to the power of an odd number. Looks like that in general. Whereas if you have x to the power of an even number, generally looks like this. If we do the horizontal line test here, right, it says that a function is 1 to 1 if and only if no horizontal line intersects the graph more than once, right? So here we get just an intersection once, whereas here we would get 2 intersections, right? Therefore, it's not 1 to 1. This one, therefore, it is 1 to 1. Yeah. So that's just a test that you can do, especially if you're graphing in Desmos, right? Just remember, okay, if I can draw lines and I'm only intersecting the graph once at each imaginary horizontal line, then it is 1 to 1. Whereas if I'm intersecting twice or more than twice, it's not 1 to 1. Unless I've restricted the domain, right, like we saw in one of those examples, then it might be 1 to 1 in that little section. So we're not going to talk about these, but because it's just given graphs and figuring out if it's 1 to 1. But what I do want to talk about is the inverse of a function. So the inverse of a function assumes that the function is one-to-one. So that's what we established first. Okay, we need to be able to show that something is one-to-one before we're able to find the inverse. So let f be a one-to-one function with a domain A and range B. So then its inverse function, which we denote by f to the negative 1, has domain B and range A. So notice that they've switched and is defined by, so the inverse of f at y is equal to x, and as long as f of x is equal to y for any y in B. Now this is a little bit weird to read, right? But all it's saying is that the inverse is going to undo the original function, right? So everything that you have to do to kind of undo it, if there's multiplication, you have to divide. If there's addition, you have to add, but also in the proper order. So the inverse function is essentially the reverse of the original function. So here is where we start and say, okay, if we found an inverse, so if f is one-to-one with a domain A and range B, the inverse function satisfies the following cancellation properties. The inverse evaluated at the original function has to give x. This, notice this is just the inverse composed with the original function. So here, this is just f inverse composed with f of x. And then this here is just f composed with f inverse of x. Okay, so we use function compositions, right? It might be easier to look at it this way, or I actually prefer this way. So if I plug in f of x into my inverse, what I should end up with is x, right? And then I know that I have my inverse, right? Same thing, if I plug in my inverse into the original function, I should end up with x again. And that's how I know that I have my inverse. So we confirm that we have found f inverse of x by checking to make sure f inverse, make that look a little bit nicer, of f of x has to equal x, and you have to do both. F composed with the inverse also equals x. So what this is saying is that we use function composition to confirm we have found the inverse. We have found the inverse. Okay. So this is called the cancellation property. I'm not really going to call it that, but I will ask you, okay, and then confirm that this is in fact the inverse. So before we actually find the inverse, let's do one of these problems here. So here, use the inverse function property to show that f and g are inverses of each other. So here, we're given f and its inverse g, right? And then vice versa. So f is the inverse of g and g is the inverse of f. So they'll always have that kind of flip-floppy relationship. So let's see here. Let's do 45 just for a bit of a challenge, because we already know we have to do function compositions. And so let's do 45. So if f of x is our original function and g of x, we're treating it as the inverse, or vice versa, right? G of x is the original and f of x is the inverse of g of x. Either way, we have to confirm using these properties, right? And so 45, what I need to show is that f of g of x, and I'm just going to go ahead and do it, and then I'm checking to see if I get x to fall out. So f of g of x is 1 over g of x minus 1. G of x, so now I have 1 over g of x, which is 1 over x plus 1, and then minus 1. Luckily, that's going to go away. Otherwise, I'd have to find common denominators. My dog's like Struggle City over there. She likes the blanket over her head just right, so she's having to do it on her own. So here, we've got 1 over x plus 1 minus 1. That's going to go away. And so I get 1 over x, which is 1 over 1 times x over 1, which is just x, right? That's what we were wanting to show, that f of g of x, you end up with just x. So now I have to check the other way. Does g of f of x also give me an x in the end, right? Once I've simplified, then, you know what? I'm gonna do them side by side here. Maybe I shouldn't have written so lofty there. So now I'm gonna check g of f of x. G of f of x is 1 over f of x and then plus 1. Okay, 1 over f of x, 1 over x minus 1, and then plus 1. Okay. I'm going to simplify this fraction over a fraction before I go ahead and add it to 1, because I'll probably have to find a common denominator. Or you can multiply this by 1 over x minus 1 over 1 over x minus 1, but that feels really nasty, so I'm not going to do that. But I get 1 over 1 times x minus 1 over 1, and then plus 1 becomes x minus 1 over 1 plus 1. Hey, looking nice, right? X minus 1, oops, x minus 1 plus 1 is just x again. So now we've been able to confirm that because I was able to show that the compositions either direction, right, just give me an x in the end, well, by those cancellation properties, g is the inverse of f and vice versa. So what we're going to say here is that therefore, by the cancellation properties, g of x is the inverse of f of x and vice versa. Nice. Good. So how do we find this inverse? How to find the inverse of a one-to-one function. So the first step is you have to make sure that you have a one-to-one function, which we know how to do now, right? So how to find the inverse, put it here so we have nice and big. There are a couple of different ways that we can do it, right? So how to find the inverse of a one-to-one function? You could write y equals f of x, right? So that's just writing f of x normal, we've been saying, okay, well, if you see f of x, you can probably just read it as y unless there's more than 3 variables. We're not going to deal with that. I don't know why I said that. It's not going to happen. So y equals f of x is typically how we can just read f of x. And then you're going to solve this equation for x in terms of y. So you're going to shift this whole equation and just solve for x, right? And then in the end, you're going to have x on one side and then y's on the other side. And then what you're going to do is you're going to interchange x and y. And then the resulting equation is y equals the f inverse of x. Okay. Another way that we could do this we could find the inverse is just doing this in a slightly different order, where I start with interchanging x and y, right? So you write y equals f of x, 1, write y equals f of x, 2, then because I like to solve for y, and so instead of x, but doesn't matter, I'm just kind of reversing the order or changing the order a little bit. So then I interchange x and y, and then I solve for y instead of x. Interchange x and y, and then solve for y. The resulting equation is y equals the f inverse of x. Okay. So it doesn't actually matter. You end up at the same thing, but I just want to introduce you because I have a feeling that this is how I was taught when I did it in high school. And so I just feel like that's what I should be telling you guys too, if you've had it before, or if this is how you did it, then either way, we should end up at the same inverses, right? And so it doesn't actually matter. So let's give this a go here. Okay. So let's do 54 together. Right. So 54, f of x equals x minus 2 over x plus 2. So if we're following these steps, right, you're going to write y equals f of x. So y equals x minus 2 over x plus 2. So step 1, y equals x minus 2 over x plus 2. I'm going to follow my steps, but if you follow the other steps, it doesn't matter. Then you would just be solving for x here, and then you'd have to switch x and y. But I'm going to swap, so wherever I see an x, I'm going to write y, and wherever I see a y, I'm going to write x. So here, I'm going to have x equals y minus 2 over y plus 2. Okay. And then now, I have to solve for y, right? So slowly but surely, I'm going to try to move everything so I've got y on one side and x is on the other side. So this becomes x times y plus 2 is y minus 2. Because I want to get x, all the y's put together, right? What I'm going to do is I'm going to have xy plus 2x equals y minus 2. Now I've got y here. I'm going to move this y over here and this 2x over here. And so I get xy minus y is -2 minus 2x. Right, just doing a switcheroo. This is just quick algebra, right? So we should be pretty comfortable by now doing this kind of stuff. Right? If not, you'll get plenty of practice doing these inverses. So now I'm able to collect a factor out of common y. So I get y is x minus 1 is -2. I can pull out a common -2, and maybe that's what I'll do. -2 times 1 plus x. Divide both sides by x minus 1. So y is -2 times 1 plus x over x minus 1. So now this is my inverse. F inverse of x. Okay, so if I've said that this is my inverse, okay, so here's my original function, here's the inverse of that function. What I need to do is I need to show that it actually is the inverse by doing those function compositions, right? So using that cancellation property. I'll do this one here. Show the F inverse of x we found is indeed the inverse of f of x. Right. What this says is we have to use the cancellation properties. So just as a reminder, right, f of x was x minus 2 over x plus 2, and what we're claiming to be the inverse is -2 times 1 plus x over x minus 1. Okay. So what I have to show is that f composed with the inverse, right? You can tell this is going to get nasty because I'm going to have to plug this in for each of these x's, right? So f composed with the inverse has to equal x, so it all has to cancel out to become x. And same thing, f inverse composed with f also has to boil down to make x. So here we go. F composed with the inverse is going to be -2 times 1 plus x over x minus 1. Really careful with your negatives. All minus 2 divided by x, which is now going to be, oh, you know what? I guess I skipped a step. I didn't write out the f inverse, but maybe that's okay. We've done enough maybe to see what's going on here. Right. F inverse has already taken the place of x's. So I've got a fraction minus essentially a fraction, so that means I have to have a common denominator, as well as down here I also have to find a common denominator. And so this becomes -2 times 1 plus x over x minus 1 minus 2 times x minus 1 over x minus 1. Okay. Dealing with the numerator and denominator kind of side by side, right? Finding these common denominators so that I'm able to simplify. So I get -2 times 1 plus x over x minus 1 plus 2 times x minus 1 over x minus 1. So now I've got the same common denominator down here. So this becomes negative 2 times 1 plus x minus 2 times x minus 1 all over x minus 1. Then divided by negative 2 times 1 plus x over x minus 1 plus 2 times x minus 1 over x minus 1. Oh, I can combine that common denominator, sorry. I've got a fraction over a fraction. We have to be so careful here, right? And so what I might want to do is I might want to simplify this a little bit, or see if I can simplify this and this before I start flipping stuff. And so I get negative 2 minus 2x minus 2x plus 2. Negative 2 plus 2 is going to cancel out, and then the negative 2x minus 2x makes negative 4x, but it's all over x minus 1 divided by, and then doing the same thing down here, expanding things out to see if anything falls out. And so I get negative 2 minus 2x plus 2x minus 2. Okay, so now it looks like negative 2x plus 2x is the one to go away. And this is all over x minus 1. So this simplifies to negative 4x over x minus 1 divided by negative 4 divided by x minus 1, which is negative 4x over x minus 1. Now I've got a fraction over a fraction, and it's nice and easy. I can just flip and multiply. And so times x minus 1 over negative 4, x minus 1 divided by x minus 1, that's going to go away. Negative 4 divided by negative 4, I'm just left with x here, right? So equals x. I've got a page break, so that's why I'm keeping it on the same page, because I know I'm out of time. But, right, so this equals x, so it all works out. So now you would need to do the same thing where you have the inverse on the outside and the function on the inside, right? So now you're going to plug in x minus 2 over x plus 2 wherever you see an x in the inverse, and same idea, everything's going to fall out, and all you're going to be left with is x, which confirms that what we found to be the inverse is the actual inverse. So I'll leave that for you guys to work through on your own, and then we'll finish that next day. Any questions? This stuff is tedious. It's not hard because we've worked so much with fractions, and our algebra should be pretty solid by now. But you do need to take your time. You do need to be so careful. All right, I'll stop this recording here.